So this is how you define two different molecules that have the same chemical formula. So, you know, H3O or H3O could be like, I don't know, it's possible that maybe there are, you know, separate ways to connect these. So let's see here. There is isomers constitutional. This is different connectivity in the same formula. So all that's happening here is this is your parent chain of 1, 2, 3, 4 carbons. Chloro is at the second position. This is your parent chain once again of 1, 2, 3 carbons. Chloro is at the 4 position. Or I guess the 1 position now. But basically all that you've done is same chemical formula. There's 4 carbons and 1 chlorine, 4 carbons, 1 chlorine. They're just, the chlorine is in a different place. Now stereoisomers are referring to the way it's facing. Remember, these are 3-dimensional molecules put on a 2D piece of paper. So there's actually a directionality to all of these atoms. So now this chloro, that's just at the 2 position in both cases. Now here it's in a wedge, it's facing towards us. It's a dash, it's facing away from us. Same chemical formula, same connectivity, but now they are mirror images of each other. And diastereomers are, they're not in your mirror images, but one of them has now been flipped. So this chlorine is still facing the same way as that chlorine, but this one is different from that one. And those are not mirror images of each other. These would both, this would have to be, these both would have to be flipped in order for them to be a mirror image. Isomers, this is same formula, different connectivity. This is just a more detailed example. So the bonding is different. You can see it at the end here. And here, the O is in the middle. Same formula, C2H6O, but totally different molecules, total different reactivities. This is showing you how good it can get. This is the formula C1, 2, 3, 4, 5, and I guess H10 or H12. And then C5H12 can mean that. 6 different possible cases. Imagine if it was C6 or C7 or C100. I mean, there's literally thousands of different molecules you can get with the same chemical formula. And once again, so this is once again same molecular formula, different connectivity. So this is, here we go again. Here's C6, all these different phrases. Cyclohexane. This is an cyclopropane. I mean, it's crazy different variety you can get. And this is saying the molecular formula are the same, but the IOPAC names, remember, are different. They're constitutional isomers. Yeah, so you can see. Yeah, so yeah, formula is the same, but totally different names. I mean, look at this name versus still C6H12, C6H12. Look how different this name is from that. Stereoisomers, not. So different arrangement. Yeah, so now we're dealing with. So here we have, you know, this methyl group is here. This chlorine is facing out at us. So now you have this left side is the same. You can see that it's that, you know, chlorine H, CH3, chlorine H, CH3, but look at what's happening here. This O is in the plane of the paper, this H is sticking out of this, the Br is facing away from us. But now if you rotate this whole molecule 120 degrees, this Br would now come to this position, this H would go to that position, and this OH would go to that position. And that's exactly what we see here. And this is once again, just rotating everything around once. That's how you get this molecule. So these are conformational isomers. Same connectivity, just different arrangement. The bonds have been rotated. These are configurational isomers. So now you can see that cis is referring to the same side. Formula, same connectivity, everything, but now they're just facing opposite ways. Or now they're just across a double bond, they're facing opposite ways. This is, I know, this is if it was a cyclobutane rings. Here they're both above the ring, now they're across the ring. This is, call it another way. You know, you see it's cis, 1,2-dimethyl cyclohexane. This is the actual names of the molecules, trans, 1,2-dimethyl cyclohexane. Enantiomers, and these are now non-superimposable mirror images. So you can see that both of these chirality centers have to be switched in order for them to be enantiomers. So you can see that R, which remember if H is facing away, the highest ranking constituent, second highest ranking, third highest ranking. So it's, this is R. You would just R and R, they both get switched, S to S, enantiomers, enantiomers. If one of them is switched, they are diastereomers. So here R switches to S, but R stays the same here. So not enantiomers, diastereomers. R and R, there's still one R, diastereomers. So enantiomers are a very special case of diastereomers that everything has to be flipped. This is, yeah, so you can see once again, I mean, this is just as if you were to put it in the mirror, totally separate molecules, even though they have the same conductivity. This is kind of showing. Here, this is a wedge H, wedge Br, different molecules. Let's see. Mirror images, epimer. Yeah, so now this is another case of diastereomers. Now, if only one of them is switched, they're still diastereomers, but they are epimers. They differ at one and only one chiralated center. So in this case, this chiralated center is different. These are epimers. They're also diastereomers, but now they're more specifically epimers. Center has been changed. This is another example of an epimer. So RRR, only one of them is switched. Now it's SRR. If this went from RRR to SRS, no longer epimers, they're still the diastereomers.